Hi, everybody. I'm Mattia Lecci. As Eugenio said, I'm from Keysight Technologies. I will be sharing this talk with my colleague, Francisco Garcia. And it's going to be about 6G DevOps. We will talk about later about what this is and what we've done in this regard. So first of all, I actually wanted to talk a little bit about us, right? Because I'm not sure that everybody knows who Keysight Technology is, what we do, and what is our involvement in research activities. So just as a startup, a brief history of Keysight Technologies. We started actually from HP, Hewlett-Packard, back in the 40s. It was a very, very big company, right? In the end, towards the 98, 99, they decided to separate the part about electronic measurements and measurements in general, testing in general, into a different company, retaining just the PC printing and consulting part into the original HP. And this spin-off was called Agilent Technologies. The spin-off grew more and more, and it was working around not just electronic measurements, but also about life sciences. And the two businesses were big enough by themselves that they decided again to split and keep life sciences and let's say biological testing equipment for Agilent, and separate in a second spin-off the electronic measurement and testing components part. And this is where Keysight was born in 2014. So it's actually a pretty young company by itself, if you do not count the entire history of this company. What do we do? We do everything from commercial communication. We also do stuff on semiconductors, but also automotive, energy, aerospace and defense, IoT. So we really cover a broad spectrum of topics, and we help companies and manufacturers from everywhere from the design. So we have some design software for electronics, for photonics, for even mechanical stuff lately, to emulation, prototyping, testing, manufacturing, optimizing. And we have different systems. We go from hardware systems, and some of them will be also used in the results of this talk. We have some software only parts, and they will also be mentioned later, some of them at least, in this talk. We also offer some services. So it's a very, very big company. It's that covers lots of countries around the world. Given where we are giving this speech, right, I wanted to focus a bit more on the European side, right, of the Keysight R&D, where we are. You can see here a small map of where our main R&D locations are around Europe. I think there are around 15 to 20 R&D centers around Europe. Some are smaller, some are bigger, but yeah, different centers cover different topics. For example, here in Milan, right, where I'm based, we mostly cover commercial communication. Frankie, my colleague, is in Edinburgh, and he also does mostly 6G wireless solutions, right? But yeah, we cover everything from 5G and beyond 6G. We go to AI, quantum. We also do ASICs, DSPs, photonics, imaging, modeling, anything really. And we collaborate a lot, right, within our cooperative projects. Just in talking about Europe, not even the rest of the world, we touch 28 countries with our collaborations. We've had collaborations with more than 47 universities, at least when these slides were made. And also 31 R&D institutions and metrology institutes. We have, I think, around 10 to 15 network operators and 25 or 30 industry leaders in telecommunications sector. And we also collaborate with about 100 high-tech, small and medium-sized enterprises. You also see down there in the bottom right, Restart, right? We are also part of this Restart Foundation. We are part of Sparks, Cascade Call of 6G YNet. But today we will not be talking about what we're doing there. We're actually going to talk about slightly different topics. What I wanted to mention as well here, since it's one of the big projects, right? One of the big European projects where we are involved, and we are actually coordinating. Our manager, Frankie's, and my manager is one of the coordinators for this European project. Right here, we basically create testbeds. We have 4 different locations around Europe. I think we have Berlin, Oulu, Athens, and Malaga for centers where we can do experimentation and we can support other people's and other groups' research, right? And we do everything here from energy, right, at the RAN, at the core, the UE, anything really that is around energy, visibility across the backhaul and the frontal interface, anything ORAN pretty much. And here we will be talking mostly about ORAN in this talk specifically. AI, right, from creation of data sets to testing of XApps, RApps, or also deployment and so on. Deterministic networks, digital twin is another big topic in the last couple of years. Cybersecurity, we have a few cybersecurity experts in our group as well. RIS, right, reconfigurable intelligent surfaces is another very big topic right now within our group. At least we've done a few measurement campaign, and we will also do more, as I know also people in Restart are doing something similar. NTN is another topic and so on. So just, if you want to take a look at that, I put a QR code that simplifies your life into getting to the 6G Sandbox website and check what can be done, and in case you want to engage with us, collaborate, and so on. Okay. So this was just a brief introduction about Keysight technologies, but I think I'll just leave the floor now to Frankie for the 6G DevOps introduction.
So I'm going to give you a very brief overview into what we mean by 6G DevOps, okay? Covered in 4 main areas, essentially, which is what is intended by continuous integration, development, deployment, and testing. What is it that 6G brings into the party that makes things a little bit more interesting or more complex? A little bit of an overview of what we call our core architect, which is essentially our various components that we use through simulation and emulation that we can now bring into a concept of DevOps to facilitate the mechanisms that we proposed above, and clearly highlight the importance of test automation, as you will see, because there's so many different configuration parameters that you can put a device under test through, and so many options that without actually doing this in an automated fashion, you'd be there years trying to cover all the use cases and so on. So the first thing that we have is that Open RAN is intended really for a multi-vendor deployment scenarios at scale. And with that, it brings in many, many challenges. Obviously, you have the notion of being able to integrate and troubleshoot these different components from different vendors as they interconnect. They're trying to achieve better performance, more cost efficiency, and try to work out the big thing now, which is energy efficiency. They're dealing with disaggregated hardware. They want to be able to optimize both the hardware and the virtualized software components that run either in virtual environments or in cloud native, okay? And they want to essentially speed the cost of the evolution of these functions, virtualized network functions or physical network functions, to get them to market very early on. And an area that I don't have much expertise about, and neither I think Mattia, but we won't be talking about, which is critical as well in this space, is obviously the idea of security. All this multi-vendor capabilities to integrate, to collaborate, to connect, to talk to each other, we really have to push the boundaries as well to test its security capabilities, make sure that it can't be intruded. Those are the kind of challenges in this multi-vendor environment. And then from test and integration, we kind of try to address this through pre-integration testing, where we're looking at the conformance of the compliance of those virtual functions or physical network functions through the interfaces that they have to make sure that they interoperate, they perform a certain level. And that allows essentially vendors to be selected by different operators on depending on their capabilities. Okay. Then you could also do end-to-end integration where you can kind of evaluate those functions against others, how they perform against other functions, etc. So you're looking at pre-deployment and post-deployment semantics in terms of those functions, okay? And then clearly you go out towards the field deployments where you want to have this running in the real environments, right? And this has to be, performing to certain levels and being optimized. A lot of this essentially starts from this notion of plan, code, build, test, release, deploy, operate, and monitor, which are traditional functions that you can apply to just software services, but here you have a disaggregated environment. So it makes this idea of continuous integration, continuous delivery, and continuous deployment a lot more challenging, in particular for operators. But because of this interoperability issues and so on, you now want to also introduce continuous testing. And that brings in serious challenges into this whole pipeline of CI, CD, CT. And that's essentially what we're kind of looking at. But now when we start looking at 6G, well, what is 6G all about? It really is all about AI. So you have AI native mechanisms that could be introduced into the 6G fabric in terms of neural transceivers, ability to do things in protocol stacks, etc. You have AI that could be brought in to control the resources and optimize the resources of a 6G network or a RAN network. Okay, so that's AI for the 6G, if you like. And then you have the 6G resources or the Open RAN resources as well that can now be utilized for assisting AI applications or services. And there are many of those in terms of automotive, home assistants, all that kind of stuff that can be brought in. So this brings in this complexity of like, this is all about AI and ML. How do we then apply those CI, CD, CT testing communication techniques to AI and ML algorithms? So most of our tools, like I say, are simulators and emulators. We tend to work on bespoke synthetic data that can be used for training those AI and ML models. We can use that as well to test those models, validate those models, etc., do some benchmarking, and essentially create high fidelity models that can potentially be brought into either digital twins or be explored in the real networks themselves, etc. A lot of the focus, again, is benchmarking, profiling, and characterizing those AI/ML models. And the idea as well too is to bring in the security aspects to make sure these things work and that they are integration ready. So if we talk about AI and ML, the main driver for these things is data. If you don't have data, you cannot train an AI and ML algorithm. And in the communications sector, we're not looking at images of cats and dogs. We're not looking at the multiple verses that have been written across the World Wide Web. We really need data that is related to cellular networks. So there's two ways of obtaining it. Live data, which is very difficult, very costly. It has serious concerns in terms of allowing data privacy and everything else out of there. So it's sometimes very hard to acquire. Or we can work on synthetic data, which is where we're at. Once you've got that data, then you can use it to train your AI and MLs. You can work on the design, you can develop your algorithm, you can test your algorithm, you can optimize it. And when you're happy, you can try to integrate it into target environments, which again could be in the lab. It could be a lab deployment like our 6G sandbox, or it could be into digital twins that also allow you to connect to some real world examples. While you're doing that, again, you're trying to benchmark and do explainability of your AI algorithm. Why is it making decisions? Again, collecting results and measurements and feeding it back to the full synthetic data to try and improve your data services, etc. All this kind of pipeline working together as part of a way of accelerating the training, the testing, the validation, and benchmarking of AI and ML algorithms. And we use kind of this pipeline of data generation and ingestion and reproducing in our 6G DevOps platforms to facilitate this acceleration. Okay. So the core architect, which I kind of mentioned, is the various different solutions that we have developed in the past for testing either physical network functions or virtualized network functions, are highlighted here in red. These are different solutions that are used to test various different types of physical functions or virtualized network functions. And the direction of the arrows kind of tells you the direction in which they test. So for example, if we look at our USIM, which is a radio, open RAN radio emulator, simulator, it is used to test upwards towards the DU, CU, and the core network, while load core can test essentially the core network, but equally with core SIM, which is one of its flavors, test downwards towards the air interface, if you like. Now, most of these devices or solutions have been used to test these functions in isolation, joint together, or end-to-end. But the majority of them have been used traditionally today for conformance and interoperability testing. In the idea of DevOps, we're taking these functions, we're combining them together with test automation to be able to create us this very rich, very high fidelity data that we can use to benchmark, test, profile, train, etc. AI and ML algorithms for these functions. Okay. As I mentioned, test automation is key here. And for that, we've been using OpenTAP. OpenTAP is an open source framework that allows you to create these test plans in terms of execution of steps that you're going to be running once you got all these components collected together and ready to go. So you have plugins that will allow you to, or you can create plugins that allow you to control your device under test. So different network functions, different virtualized functions, radio physical functions will provide by the vendor different capabilities to be able to control them. We can create plugins to control that, to test, to put them through test sequences. The test steps essentially are described by the OpenTAP framework, but equally we can create custom plugins or use existing plugins to control our instruments and other instruments that are required to essentially wrap around these functions to create the rich data to test them. And there's plenty of output listeners, right? So you can send your results directly to databases, you can collect in CSV or text file or create custom ones, as well as create user interfaces. You will see some of this in action when Mattia kind of explains some of our use cases. But those are the essentially major steps that we're kind of looking for in terms of 6D DevOps. Originally, the functions were used for conformance interoperability testing. We're putting this together as a solution to do wraparound test that will allow us to give us very rich data generation for not only performance benchmarking these functions, but also to be able to train AI and ML algorithms to do optimizations with these functions. But all of this requires automation. Okay. Now I'm just going to quickly go over a couple of these platforms so that you can see what they look like. Try not to spend too much time on these. So here we're using, this one's how we test essentially the physical network functions. So this is a radio unit, which you can see here at the right, okay? And this is wrapped around with what we call an ODU emulator, which you can see around here at the bottom. And then we have a signal generator for uplink signals and a signal analyzer that can look at the downlink signals. In other words, the signals that will be going over the air from the DU over the air to UEs. Essentially, we can analyze them, but we could also look and analyze as the input signals. We have some software that allows us to create the test vectors in terms of IQ for the signal generator and PCAP files, which represent the C plane and the U plane of the ORAN front haul interface as test vector sequences that we can run towards the ORU. The control plane essentially is indicating to the radio unit what to do with the IQ that it receives in the downlink and what it expects to receive in terms of IQ in the uplink. We can add a power analyzer again to see the draw of the electricity to the radio unit when we're running it past these tests. This is, for example, very important right now in the AI RAN Alliance when they are looking at different optimizations in terms of sleep modes, etc. that could be used to control a radio unit. So we can put the radio unit through those stages and measure the power draw to see how efficient those different optimizations are. Okay. For virtualized network functions, which is a bit more of the subject that we're going to cover here today, these are the components that we kind of use. We have a server, a COTS server, where we run the virtualized network function on. And this is wrapped around with our cloud native simulators, depending on the function, which one we use. Most of the time we're using Core Sim, which simulates the core of the network. And then at the other end, we have the RU Sim, which can pretend to be 2 radio units and several thousands, up to 50,000 UEs with air mosaic and so on. We can add other components like a network emulator in between the front hall interface. And this allows us to introduce anomalies at that level. So we can delay packets, we can corrupt packets, we can get different prioritizations, etc., creating anomalies to see how those functions behave to that. We have a digital sniffer if you want to look at the open front hall and see the impact that this is having on the U plane and the C plane. And then equally, we have a power analyzer that allows us to draw current on the running BNF in isolation on the COTS server to see how many, how much power is using based on how we're pushing it up to its maximum load capacity, restricting it with CPU utilizations, frequencies, etc. And most of this is controlled through test automation, as Mattia will show us later on. Okay, so this is the server where we run our simulators. This is the server where we run the virtualized network functions. This is essentially the network emulator, and this is the RU sync capability that connects over the optical front hall to the server. Okay. So test configurations. This will show you highlight why you need some kind of automation to then run this test, because there are so many different parameters from the cellular configurations to the front hall configurations in terms of bit width and compression schemes and C-plane and so on. Many different configurations that without automation, really, you can't run the many tests that you probably want to do. Okay, so like I said, this is very dependent on in this case, the virtualized network function. Different virtualized network functions will be described, telling you what is the maximum bandwidth they support, the maximum number of layers, the maximum number of UEs, whether they support FTD or TDD. Okay, we run profiles, so we create test configurations which are kind of inspired by the interoperability profiles of working with 14 O-RAN Alliance. So we describe these parameters and how we're going to test these things. And we run test campaigns, which we apply across 3 levels of layers. One is coarse sweeps, where we run very coarsely across certain test step sequences, so we can create some benchmarks. We then use best case sweeps, where the VNF is kind of lightly loaded and working in ideal conditions to see how well it's doing. And then in worst cases, where it's the VNF is running at its max capacity and see how well it's doing. Then we carry out sweeps, where we kind of test downlink throughput and uplink throughput, a number of UEs in bursts of 60 seconds, right? And we separate every downlink burst is essentially separated by a 5-second interval, so that we can collect results and compare. And equally, we split the downlink with the uplink over a 20-second interval. So this is uplink sweeps that you see here. We have 7 of those, and we have 10 downlink sweeps. Here, this chart is essentially using the power consumption. We're sweeping through these different throughputs. We're increasing the throughput, as you can see, all the way up with each burst, as an example. So overall, we can test the virtualized network functions in that server as bare metal in a virtual machine, or in containers such as Kubernetes. There's a lot of interest in terms of testing across these dimensions by different vendors, because they use different technologies to deploy these BNFs. So there's a lot of work that they want us to do in terms of comparing how long does it take to bring up a VNF, to get it up to optimization, and to essentially close it down as well. Okay. Overall, some of the examples that you will see that Mattia is going to be talking about, we collect over 300 metrics at the moment. So it's a real hard graft. Let's just collect all the metrics without thinking about it, without using any cleverness in terms of AI/ML, how to do this. But it just shows you why we need test configuration, but the richness of the metrics that we can collect that can then help also train AI and ML algorithms, as we will see. Okay. And there are essentially, if we look at all the parameters that we kind of will see later on, there's a potential for 2,448 different configurations that you want to do a test sweep over. So hence the importance of automation. Yeah. This is an example configuration, like I say. So we kind of, this, which is for the core sweep. We specify the number of MIMO layers, the bandwidth that we want to go up to from 20 to 100, the number of UEs, the application downlink and uplink throughput, the number of CPUs that we want to allocate to that virtualized network function, okay, and how much throttling we want to apply, and in this case, the NR TDD lookout. Essentially, this core sweep allows us to identify very quickly KPIs that are having an impact on the VNF performance before we go into, let's say, best case sweeps, right? So here for the VNF, we're saying, let's just use 2 layers MIMO, let's use 20 megahertz bandwidth, let's just use 10 UEs, and then step it up for the uplink and downlink throughputs, as we said before, and some configurations of throttling CPUs and number of CPUs. And then the worst case is really running that VNF up to its limits. So the VNF that we were looking at in this particular case could only support 4 layers MIMO up to 100 megahertz of bandwidth and up to 50 UEs. So we push it to those limits and see how well it behaves. Okay. We also did a baseline performance, limiting the RAM and usage to 263 to see how these functions also performed. But in summary, we end up with 145 individual test cases, right? Each covering 10 downlink bursts with 7 uplink bursts and creating 2,465 data points. And we can see those 145 test cases here as a quick snapshot in terms of 4x4, 120, 2x2, 120, number of CPUs and the frequency where some of these test cases fail because clearly there isn't enough resources to run that BNF to be able to cater for the UEs and the throughputs. So, and again, this is a very quick indicator of the limits and the different configurations where the VNF will function or not function, okay? And at this, oh, no, sorry. So in terms of metrics, like I said, we collect quite a lot. And I'm not going to go into many details about this, just very quickly highlight where we collect metrics and the types of metrics. So on the server side, we use a lot of the Linux performance monitoring tools. So Perf, for example, to collect metrics on the CPUs, right? The utilized CPUs, the context switches, the migrations, page faults, etc. This is very valuable information to assess and benchmark the virtualized network function itself. We monitor the interfaces that are being exercised by the virtualized network function. So if it's connecting over the F1 interface towards a CU, or where it's connecting through the backhaul interface towards a core directly as a G node B, right? And the optical front haul interface. And we collect metrics in terms of transmissions of packets, collisions, errors, etc. Again, just reading the proc file system. And then finally, using the processor status, we also monitor the utilization of memory for the BNF. And those are the metrics in the server side. Then, depending on which virtualized network function, who the vendor is, and so on, they might also provide some logging or some metric collection. So here we were using SRS-RAN, and we can collect reports from SRS-RAN while that function is running under various conditions that relate to the radio link control metrics. So essentially the data radio bearer utilization metrics. That's quite valuable to try and pick up to see how things are working, how many are being set up, where they fail, where they lose packets, etc. And equally, some of the reported cell and UE metrics that it kind of gives us, we collect and correlate as well. From our own kind of emulator, which in particularly is the RUSIM in this particular case that Mattia will show, we can collect very low-level layer 1 PHY metrics related to the downlink, physical downlink shared channel and the uplink shared channel, including CRC errors, transport block errors, etc. So we can again see the impact of different loads on end-to-end services, right, at the PHY layer. Equally at the RLC, PDCP, and some of the cell level metrics, we can collect those. And I think finally, we also simulate the application. So one, you have what you simulate in terms of the cell configurations and the allocations, but equally then you want to be able to simulate different traffic profiles for different users, etc. And that is done through our application layer simulator. And at that level, we can collect lots of downlink metrics as well as lots of uplink metrics. And of course, this is kind of all automated to be able to collect these metrics and analyze them very quickly for a particular use case, as we will see Mattia showing. So I think this is where I stop, and I hand back over to Mattia, and Mattia will then talk about test automation in a little bit more detail, and then some of the use cases where we can show you some of the results that we have collected with the 6G DevOps environment.
All right, so thank you, Frankie, for the introduction. I will now proceed with the test automation, and I will show you a glimpse of results of a couple of different use cases among those that we tested in the past few months, or mostly like last year. So test automation, right? You mentioned already what OpenTAP is, which is basically this open source platform that is actually maintained by Keysight. There is the core engine, which is open source, and then there are different GUIs and more advanced features that are some of our products. But the good thing here is that basically you can control all your lab, or in this case, the specific testbed you're interested into, with a single PC. So we have, for example, a PC in our lab. I could also run it from here, from Milan, and control the lab, which is currently in Malaga, as long as we are connected to the same LAN. But for example, with OpenTAP, right, it works on packages, and you can install different packages. And there's a package, for example, to control RUSIM, UESIM. We actually created within this project a package for NE3, which is currently not yet available, but work in progress. We also created an open source package for the SRS-RAN GMB. That's actually open source as part of one of the projects we were working on. We also have a package to control load core in general, and coursing, which is a specific instance of load core. And there should be also something specific for power analyzer, but we were just using more direct, what we call skippy commands to control it. And basically, with this test plan, I will show you later in details, you can control and orchestrate this whole thing into a very, very complex setup. So just to give you an idea, right, of OpenTAP, you have different flavors. On the left, you can see the open source version. It's called TUI, the text user interface. You can simply run it from your terminal, and that's what you get from the open source version of OpenTAP. Here, the link in case you're interested. And on the right, there are two more advanced graphical user interface. On the top right, you see the pathway test automation, which is the desktop version of the GUI, and on the bottom right, you see the test automation cloud, which is actually running natively from the browser. And then you can simply install a runner in any PC that you want and give permission, for example, to your colleagues. We have a group where we share the permissions of this testbed, and then we can schedule campaigns and test plans and collect results via the graphical user interface, via the web, and so on, which is really nice. But this is the sort of complexity that you can get to when dealing with these things. So as we mentioned, right, there are a few components in this testbed, and they have to be carefully orchestrated. So, for example, you see number 1, 2, and 3 are the 3 main parts, let's say, of the test plan. And here highlighted, you can see some of the setup, right? You define some results folder, scenario, and so on. You can, clean up the DUT and all that. You can check the status of some components. For example, since we are talking here about VNF testing and specifically the DU plus CU VNF. So VNF that contains both the ODU and the CU in a single piece of software in the COTS server connected to RUSIM, which simulates the ORU. It's one of our solutions to simulate the ORU. In the middle, there is a PTP grandmaster, which is a switch in this case, basically that gives the timing between the RU and the DU. And we can check, for example, the status of that PTP switch in case there is an issue, or in case you want to record or log the status of the PTP synchronization between the different components, in case later on you find some issue in the results and you want to go back and check. What we do here actually is to basically turn off everything at the end of the test, and turn on everything at the beginning of the test. So every single component here, core sim is started, the GMB started, and RUSIM is started, the test is executed, and so on and so forth. And at the end, you basically stop all components and collect logs and results for those components. So everything here is sort of orchestrated, and as you can imagine, this can take a lot of time, right? Frankie was mentioning before, we have 10 downlink bursts for this specific case, plus 7 uplink bursts, 1 minute long each. So just the bursts themselves are 17 minutes. Plus imagine the bringing everything up and running, get the connectivity, get the synchronization, and so on. Perform the test, do the logging, downloading, and so on, closing everything. This takes 25 to 30 minutes for each one of those 145 tests done. So you can imagine, as Frankie was stressing before, there is a need to automate these sort of things. Otherwise, this can literally take back-to-back 2 or 3 days worth of tests. I now want to bring you to finally the maybe more interesting part, right, where we show you a few results, just very simple results. We're not going to go through all the details. We actually have submitted a few papers. So these are coming from different projects. So we submitted a few papers, a couple of journals, a conference that are still under peer review. So I cannot share the full results yet, but here, just an overview of what we've done. So one of the possible use cases and one of the maybe starting point was to check how the VNF behaves under non-ideal condition, right? You have a baseline setup, and then you reduce the power of your setup. So, for example, imagine our server has 2 CPU sockets. The COTS server where the VNF is running, it has 2 CPU sockets, and each one of them has 48 CPU cores. The VNF for performance critical issue needs to run on a single CPU socket, so it has 48 CPU cores to use. So what we can do is take this VNF and allow it to use either the full 48 cores, or just give it a portion of these cores, 25, 24, 12, 6, whatever you want. Or you can imagine the server for this specific CPU can run up to 3.9 gigahertz, but we can reduce, for example, the CPU frequency. And you will see later why this is done. Well, as a spoiler, this greatly reduces the power usage of the server, which could be interesting also for power efficiency purposes, as long as everything works. Or you can imagine in a real deployment, you have a server where you will have multiple VNFs, right? When people want to sort of centralize all the processing, they will probably have some server put somewhere in the city where they do lots of processing, and thus each server will host multiple VNFs. And so they will have to share resources between number of CPUs, RAM, and so on. So what happens is, for example, we also reduce the available RAM for the single VNF. So very simple tests, well, four, right? A baseline and a CPU limited scenario, CPU throttled scenario, so lower CPU frequency, and a memory limited scenario. So in this case, for example, we study a cell with a 4-layer MIMO, so 4x4 MIMO, with 100 megahertz bandwidth, so subcarrier spacing equal to 30 kilohertz. And in this case, we're just studying what happens when we have 10 UEs connecting to the system. The UEs are actually simulated by RUSIM. So RUSIM not only emulates the ORU as a frontal interface device, but it also emulates everything from the ORU down, meaning that it also emulates the air interface and as well as the UE. So the entire UE signaling is emulated there, from the attachment to the registration, PTU session establishment, you can instantiate applications, you can exchange data and so on. So you can really do very advanced tests with this tool. So for example, one thing that you can observe is what happens to the number of connected UEs, right? So on the left in these plots, I removed the part of memory limited scenarios because that's a topic on its own. You will see results later, but starting from the left, you see the baseline scenario, right? So 48 CPUs, so 48 CPU cores, really. I will just call them CPUs from now on. And the CPU running at 3.9 gigahertz, so the maximum frequency allowed for this system. You can see that at the beginning, all the 10 UEs are able to attach, and they stay connected without any kind of issue throughout the whole duration, which is around 25 to 30 minutes, as I mentioned before. And nothing happens here. That's great. What happens if you reduce the number of CPUs from 48 to 12 for this specific VNF, for this specific COTS server? Well, you start seeing something weird, right? You start seeing towards the middle, towards the end, UEs are not happy anymore. Something starts to happen. It seems that some UEs are disconnected, maybe even all the UEs are disconnected, and then they try to reattach. They are successful as doing so. They proceed a bit, then some of them lose again the connectivity, then they reattach, so it's not very stable. So we understand that you have to be very careful about reducing the resources to VNF, and this is also something that you can quantify if you run a good sweep of these tests. And what happens with CPU throttling? Well, in this specific case, when we do a very aggressive CPU throttling to 1 gigahertz, which is the minimum supported by this CPU, you see something similar, but even more severe. UEs start losing connectivity and then getting it back, but at some point they lose the connectivity, and that's it. They're never able to come back, and the simulation just fails like that. So looking a little bit more in details, right? You see on the top side the PDSCH throughput, so the layer 1 throughput, really, as detected by RUSIM. And on the bottom side, you see the application layer throughput, so the ones that either at the core or at the UE stacks seen and emulated by the RUSIM can also give you this information. So we have a test application. It's called VDG. It's one of the in-house applications to do this kind of tests. And you see on the left, right, once again, the baseline. We're just looking at downlink here. So you basically see, if you look very closely, you will see 10 distinct bursts. they go from 1 megabit per second to 1 gigabit per second for the specific configuration. So you will see that the first few probably squeezed down to almost 0. So that's why you probably don't see the first ones. But you see that PDSCH and app layer are basically matching, except for the extra overhead given by the lower layers. So yeah, we are both around 1 gigabit per second. Going to the CPU limited scenario, you remember it was losing UEs and reconnecting UEs all the times. And here, for example, you see that something weird starts happening towards the higher the highest burst, right? Highest burst, which should be around 1 gigabit per second, and you do see on the center top around 1 gigabit per second being transmitted over the layer 1. But you see that it's not normal, it's not nice, it's not clean, it's not a clean burst. And indeed, you see below in the application layer throughput that probably there is so much retransmission, so much of a mess of an unstable DNF that this is not able to propagate through the layers. There are just too many errors, and the application doesn't actually see this burst. And so this is another thing that doesn't work for this specific configuration. And if you go on the right, you see that you cannot even reach, well, you can barely reach 200 megabit per second, 500 and 1000 megabit per second don't even appear. The connection just drops before and is never obtained again by the UEs. So you can see very, very severe issues there. Similarly to in the uplink, right? You see more or less the baseline being fine, except for a weird peak at the beginning of the highest throughput, right? In this case, uplink is around 80 megabit per second for the configuration that we chose, right? It's very downlink oriented, not very uplink oriented, but yeah, that's what we decided to do for these tests. In the center, you see weird things are happening towards the higher bursts of the uplink transmission, and even on the right, there's not even uplink burst being applied. The connectivity is lost before we even reach the uplink bursts. So you have to be very careful about how you inject issues into your system. We can even see, from some of the counters, some of the KPIs that Frankie mentioned before. For example, on the top, you see the number of CPU cores used by the VNF in the different bursts. And it's interesting to see, for example, that, on the top left, right, the unimpaired, the perfect baseline is actually using around 8 cores at most. But keep in mind, this is actually coming from CPU time converted into number of cores, not actual cores used. So this means that, yeah, if we were thinking that, 12 CPUs are more than 8, so things should work, but no. You need some process to work really well in parallel, and you need some processes to work really well in sequence. So 12 CPUs are not enough for this. And similarly, in the second row, you can see, for example, the CPU frequency. CPU frequency it also goes up as the load increases. So you see the red plot in the bottom specifically is converted to gigahertz. You see that it increases with higher usage in downlink and in uplink, and you can also see some issues here when you, for example, restrict CPU throttling to 1 gigahertz. It cannot go above 1 gigahertz, and so you see that CPU frequency stays down, but the number of cores has to go up. But still, this is not enough for the VNF to work. So some very interesting insights in these results. Finally, a quick look at the memory usage, right? We see that it's actually more or less constant throughout the full test. You will see that different cell and number of UEs configuration change the memory requirements. So more demanding cells, 4x4, 100 megahertz, for example, will require more memory than small cells, 2x2, 20 megahertz cells, for example. So that does change. And the number of UEs, 1 versus 50 UEs, it's the 2 extremes that we've done in our tests, also change the requirements on memory. But once you set that, right, there's not a lot of difference between not sending anything and sending 1 gigabit per second. So that's pretty interesting. And what happens when you set the Kubernetes pod to have a limit, for example, in this case of 2.6 gigabytes? Well, as soon as those 2.6 gigabytes are reached, the pod is killed, and so the connection is completely lost. So again, be very careful about how you set the memory limitation. I wanted to also give, let's say, a more higher level view on these resource constraints on VNF. And I will, if we have the time, I will also show you some more information about power measurements. I will actually try to be a bit faster here because I see I talk too much. But yeah, these are, for example, some of the tests that Frankie showed before, right? There is some light loading with 2x2 20 megahertz cells and heavy loading with 4x4 100 megahertz cells. The light loading is only using 10 UEs. The heavy loading is using 50 UEs, and then we test different number of CPUs, different CPU throttling, so the max allowed operating frequency. And we see, for example, some trends over when the VNF can and cannot work, when it breaks, when it doesn't break. We see that depending on the number of CPUs allowed by the system, if you reduce the number of CPUs allowed, of course, the CPU frequency has to increase in order for all the cycles needed by the VNF to be met by the system. And something similar can also be checked with the CPU throttling. So if we reduce the number of the maximum allowed frequency for the VNF, number of cores had to increase in order to keep up with all the heavy calculations done by the ODU and the OCU. I really wanted to show you some, a couple of slides, not a lot, on energy profiling, because I think it's even maybe more interesting, right? Especially going towards beyond 5G and 6G networks, where energy consumption is getting more and more important, right? On one side for environmental sustainability, but also for the costs of running the RAN. Keep in mind that if you look around for reports, I think 3 to 5% of the global power usage is within the telecom industry, and telecom operators have 20 to 40% of their OPEX costs on RAN alone. So the RAN costs a lot of money. So it has to be, it's a good idea to look into it and try to optimize the power consumption here. There's lots of things going on around energy efficiency, right? Especially in 6G, they're trying to achieve, I think, 2 orders of magnitude better power efficiency than 5G. Lots of very big numbers. But there's also, for example, AI RAN, the AI RAN Alliance. It's a fairly new alliance. It came out, I think, in the last couple of years. And in their working group 1, AI for RAN, one of the bullet points, if you download their white paper and look into it, one of the bullet points specifically says energy and spectrum efficiency. So there is another big focus on the energy, not just the spectrum efficiency, but also the energy efficiency here. But the thing is that we need to first understand how these VNFs behave in terms of energy consumption. And this is a perfect platform, the one that we built, to really understand how this can be done, right? We basically have the VNF running on a separate COTS server, so we can simply check. It's the only application running there other than the operative system, so you can really check how much power this server is consuming, and so you can try to model it from an entire system perspective, right? We have, for example, our AC power analyzer. So you could also argue that there's the possibility of using software probes. For example, Intel gives you readings about the power consumption of their CPUs, but with a a full-blown power analyzer, you can really check the entire system consumption, not just the CPU or the RAM or isolated components. So you can really check how much is required from the wall directly. And this can also, integrates well with the rest of our automated system. You can get lots of KPIs from here, from voltages, currents, but especially power, energy and efficiency, and so on. And I think just a couple of slides before the conclusions about results, right? So I think this is starting to be familiar to you. You've seen something similar or something very correlated to this before, right? When you see all the downlink bursts towards the left and all the smaller uplink bursts on the right. Just keep in mind that we have up to 1 gigabit in downlink and up to 80 megabit in uplink. So that's why the downlink is typically more demanding. But what you see here is that you can also measure your system in different states, right? In here, we start the AC power analyzer before we start everything, and we stop it after we've done everything and collected all the results and so on. So you can see, for example, what is the idle server consumption. So the server where not even the GMB is running, just staying on with just the operative system running, right? Normally in the baseline, it's consuming around 250 watts. Whereas as soon as you turn on the GMB, what does it do? Well, the GMB looks for the core, does the handshake, and then keeps connectivity with the core. And in the meantime, it starts sending SSBs over the air, or rather, in this case, towards the ORU. And just doing this without any connection, without any UE, anything going on, the power consumption goes from 250 to 300 watts, 50 watts more just to turn on the GMB. And then when actually connect UEs, I think in this case, we're talking about a 4x4 100 megahertz cell with 50 UEs. As soon as you connect 50 UEs and you start pumping through this gigabit throughput through the cell, you go to 325, so 25 more watts in the system for this data exchange. But if you throttle the CPU to 2.3 gigahertz, the numbers go down significantly from 250 to 205 watts in idle, 300 to 235 in idle GMB, and 325 to 270 at peak. And here is the case where nothing changed in any KPI that was observed. So it's something that people might, look into with more attention, whether this could be one of the possible solutions to reduce a little bit the power consumption. We've also done, much more extensive tests, but I don't think I have the time to go through them all. I'll just leave it there for a few seconds, but you've seen we've done tests with 1, 10, 50 UEs. We've done, as we mentioned, sweeps of downlink and uplink bursts of traffic. We've tested 2x2 and 4x4 MIMO, you see in blue and orange, and we tested 20 megahertz and 100 megahertz bandwidth for the cell, and you see it as solid or dashed lines. So you can really see lots of things here, lots of trends, and you can also see how our power consumption changes as a function of all of these input parameters. So it's very, very interesting. I just want to conclude, right? We're not bringing you a final conclusion on the results itself, but rather I think the focus here is more on the fact that there is this nice state-of-the-art core and testbed. We were mostly targeting for these use cases benchmarking and profiling, but also generating data sets for AI and ML. For example, we were creating these data sets with thousands of entries to train some models of, for example, understanding, asking the model whether a VNF configuration will hold these many UEs in this COT server or not, or how much power this setup will consume with this server. So that's all things that can be done and can be expanded and can also be generalized to different DNFs. And this also, becomes pretty interesting, looking mostly at RAN digital twins, for example. We showed you a couple different use cases, right? But also other use cases were done. One case was the frontal extension, where we tried to separate as much as possible ORU and ODU, so putting them on the opposite side of a city, for example, and even more, and see what happens. And so, like many different test cases can be done here. I leave again with the QR of 60 Sandbox in case you're interested, because the platform is there, so it is possible. We can discuss whether some collaboration or some usage might happen. I hoped to give you a few more references, but unfortunately the publications are still under peer review. There is almost nothing public yet, other than number 2 was not made into a paper, but we made it into a Keysight application note. It's not about this specific testbed. It's a different one, mostly looking at from the RIC. So it's a bit of a higher layer kind of thing, but still, looking into anomaly detection, AIML, and all these things. And I'll leave you down our emails in the bottom right in case anybody's interested in and wants to drop us an email for further information, or just contact us. I will conclude here my talk. And I hope you liked it. And let me know if you have any questions.